Welcome to all of you. So today I am going to explain some problems from the chapter group. So let's start our today's session, and we will start with this problem. The problem is G equals to FAB, where AB is taken from the real number R, and this is defined as FAB of x equals to AX plus B, where A is non-zero, right? And now this is obviously a group under usual composition of mapping. You can check it. So here our task is to find the inverse of this function f to 5. So since this forms a group, so that's why all non-zero elements have its inverse with respect to this binary compositions. So here, to find out the inverse, first of all we need to understand what will be its identity elements, right? So first we need to find out its identity. So let's try to find out the identity. So here the mapping, look at this function, the definition of the function. So we all know that for a group G composition, an element is called identity element if A composition E equals to E composition A equals to A. If this holds for all A belongs to G, non-zero A belongs to G, right? So then E is called its identity element. So right, using this concept, we try to find out its identity element first of all. So let's try identity. So here the mapping is this. Now suppose I am taking A1 of something using the composition sense. So here suppose A2x plus B2, right? This will be the previous function plus this is B1. So using the definition of composition, this definition, we will write this A1 of this equals to this. So if there is any doubt how I will write this, so look at the concept of the composition like here. Suppose you are given a function f of x equals to x square plus 1, right? And the next function g of x equals to sin x. Now find out f composition g of x. So to find out this composition, we will use the definition g of f of g of x, right? So we need to find out this f of g of x. So f of g of x means replace this x by gx. So in that case we will have this this is equals to g of x means sin x. So this is sin square x plus 1, right? So this will be the composition of these two functions. Now here I have used this concept. Clear? Now look at this. This is obviously an identity. Now we will compare the both sides. So A1 A2 x plus B1 plus A1 B2 equals to A1x plus B1, right? So this is our next line. Now comparing the both sides, the coefficient of this. So A1 A2 equals to A1, and here B1 plus A1 B2 equals to B1. So from here either this equals to 0 or B2 equals to 0. This is the conclusion. Either A1 or B2 equals to 0. Now from here, since A1 not equals to 0, so this implies B2 equals to 0. And why this is actually our given condition. This is not equals to 0. So here B2 is obviously 0. Now from here, since A1 not equals to 0, therefore A2 equals to 1, right? A2 equals to 1. So our inverse function, our identity. So our identity will be A1, A2 equals to 1 and B2 equals to 0. So this implies the function will be 1, 0, right? The function inverse function, the identity function will be f10. This is nothing but the function. This is the function x. So this is our identity function, which we need to understand first of all. And now using this identity, we will easily find out the inverse of this element f of 2, 5, right? So let's try to find out the inverse of this. Now to find out the inverse of this, we will use the concept of inverse. Suppose A is an element, so A prime is called inverse of A if A prime equals to E, right? So this is the inverse is obviously left as well as right inverse, right? So this is the definition of inverse. Now using the definition of composition, and so our inverse will be, the function is this, so 2x, the function is 2x, so here a1x plus b1 plus 5 equals to the identity, right? This is the definition. A prime equals to E, which I have already said that this is the definition. So from here 2a1x plus 2b1 plus 5 equals to x. So this is obviously an identity. Now comparing both sides, we will have a1 equals to 1 by 2 and b1 equals to minus 5 by 2, right? So what will be our inverse? Our inverse will be the inverse of f to 5. So we can write this as this way. The inverse will be a1 equals to half minus 5 by 2. So that's it. This is the inverse of this function f of 2, 5, right? So that's it. This is the now we will start with the next problem. So this problem I have completed. Now find the numbers of abelian groups up to isomorphism. Now find out the numbers of abelian groups up to isomorphism. So first of all, I am erasing this. There is some problem in this eraser. So now the problem is find the numbers of abelian group up to isomorphism of order 10 to the power 5, right? So you all know that up to isomorphism, the concept of this, for the abelian group up to isomorphism, actually the numbers of group is defined or determined as the number of partition. So how many partition are there for this particular this group? And so let's start to find out the numbers of groups of order this up to isomorphism. So we can write this 2 into 5 to the power 5, right? And this is 2 to the power 5 into 5 to the power 5, right? Now look at this, 2 to the power 5 into 5 to the power 5. And here the question is find the numbers of abelian group up to isomorphism of order 10 to the power 5. So now find out the number of partition of 5. So you can easily check that the number of partition of 5 is 7, right? So from here we actually get 7 abelian group, 7 numbers of abelian group up to isomorphism. And similarly for here we will also get the 7 numbers of abelian group up to isomorphism. Now since this is if this abelian, then it's finite product. So this will also be abelian group. Therefore there are 7 into 7 equals to 49 abelian group of order this up to isomorphism, right? So it's very easy problem. Now we will go for our next one. So our next problem is, so look at here, our next problem. Find the number of subgroup of the group this Z by 42 Z, right? So this is actually the group like this, isomorphic to Z42 group. Now find the number of subgroup of the group of order this. Actually, look at this group. This is obviously an abelian group, ZL. So this group is ZL. So we know that any finite cyclic group if isomorphic to ZL. So this is obviously a cyclic group because there is an element of order 42 in this group. So that's why the number of subgroup will be the divisor of this, right? So let's try to find out the divisor. How many divisor of 42? So 42 means 42 6 into 7. That means 2 into 3 into 7. Why I am finding this divisor? Because you all know that for a cyclic group, each divisor, corresponding to each divisor, we will have a unique subgroup, right? So this is the property of cyclic group, and this is cyclic group. Z42 is a cyclic group, and you may also check that there is an element of order 42 in this group. So that's why it will be cyclic group. And now the divisor means here 2 to the power, we can write this as 2 to the power 1 into 3 to the power 1 into 7 to the power 1. Now applying these methods from number theory, that number of divisor of these two equals to 1 plus 1, and number of divisor of this 1 plus 1, and the number of divisor of this 1 plus 1. So this is actually 8. So there are 8 subgroup of this group, right? So the answer will be 8, right? So its answer will be 8. So that's it, the problem, a very easy problem. And now the next problem is taken from the permutation group, the concept of permutation group. So, okay, let's try to solve this permutation group. So before solving this, first of all, you just write down a short trick or formula to find out this. From symmetric group Sn, if we calculate the cycle of length r, how many cycle of length r in this group Sn? So this is determined by 1 by r in PR, right? This is determined by 1 by r in PR. Now here the question is find out the number of elements of order 5 in S5. Find out the number of order, number of element of order 5. So order means order is actually the length of LCM of its disjoint cycle, right? So this is the order. Now we have to calculate here for this. Here we have to calculate just 1 by 5 5 P5, right? 1 by 5 5 P5. So this is nothing but 1 by 5 into 5 factorial by 5 minus 5. That means NPR. NPR means NPR in factorial by n minus r factorial. So it will be 0 factorial, conventionally 1, and this is equals to 5 factorial by 5, 1 into 2 into 3 into 4, 24. So the number of elements of order 5 in S5 will be 24, right? Now the last one. So here my last question is, so this is the last question. P equals to this. So you all see that here the given problem is related to the symmetric group permutation, and this is a permutation. So you need to rewrite this at first in the disjoint cycles. So let's try to rewrite it in disjoint cycle. And disjoint cycle means 1 to 4, 4 to 3. So look at this, 1 to 4, then 4 to 3, then 3 to 1. So 1 to 4, 1 4, 4 to 3, 3 1. So this is the cycle of length 3. And next this is 2 to 5, 5 to 2. So the next disjoint cycle, and then another 6 to 8, 6 to 8, then 8 to 7, 7 to 6. So 6, 8, 7. Now find out the LCM of this disjoint length. LCM of the length is 3 of first cycle, second cycle 2, 3. This is the LCM 6. Therefore, the answer will be, that means P to the power 6 equals to I. I means identity permutation. So here the question was, if P equals to this, find out the order of P. Hence the order of P will be 6, right? So order of cube will be 6. So that's it, my today's class, and I think you all enjoy my class, and these elements and this concept will help you to solve the problem like this. So today that's it. Thank you.